Let's talk about sorting. So sorting is this interesting thing, y'all. There are different, let's be real. Engineers have their own culture, right? Groups of humans have culture. I don't think it's unreasonable to say, for example, chess is a particular obsession within engineering culture. And that makes sense because chess is all about symbolic reasoning and pattern recognition, and that's what engineering's about, right? Also, video games are a particular obsession for engineering culture. There are few things that are as engineering culture as an obsession with sorting algorithms, all right? I hope that as I go through this, you will understand some of the joy that is talking about a bunch of different ways to accomplish the exact same task. But I also say this because, like I mentioned at the very beginning, my goal with this class is to help you demystify what I think some of those engineering cultural things are, and just recognize that this is an area that engineers expect you to know a lot about going into interviews. I will also take this moment to say, no, I have never implemented a sorting algorithm in my professional career. Have I used the algorithms implemented by, say, Java or C# or whatever? Yes, absolutely I have. But I know this is like when I teach my high schoolers this, they're always like, nah, this is one of those things that you teach us and we'll never use. And I'm like, but you will use it culturally. Eh? So I'm trying to help you out on this situation. This is an XKCD comic, which I think is hilarious because it is exactly an example of why we are obsessed with sorts. So you can see they have implemented half-hearted merge sort, fast BOGO sort, which is a ridiculous claim. There's job interview quick sort and panic sort. So I'll let you read these. They're on the slides. But yeah, like I mentioned, we're just all obsessed with sorts. So where are we generally in the course? Like I said, we've sort of finished the graphs. And by generally the fact that we finished graphs, we've essentially finished the data structures portion of this class. But this class is called Data Structures and Algorithms. And you might be like, Casey, where are those algorithms? Well, we've been giving you a few, right? We did binary search way at the beginning. Those graph algorithms, BFS, DFS, Kruskal's, Prims, Dijkstra's, right? But now we're just going to start adding in more algorithms here. And so what is an algorithm by comparison to a data structure, right? Like if we kind of go back to the beginning, an ADT is a engineering agreed upon way to describe functionality. An interface might be the way in Java you specifically codify that agreed upon functionality. So like ADT is not Java specific, right? ADT is across all coding languages. An interface is the key word in Java of how you would codify those things. A data structure would be an actual like object in code that, say, implements that ADT. And a data structure inherently is a way to group data and perhaps represent the relationships between that data, right? So a list doesn't have a ton of relationships between the data other than maybe ordering. Stack and queue, that the only relationship is just the order. That's what matters there. But then we start to move into trees. That relationship is, sort of a hierarchy. And then we get into graphs where it is just this sort of, abstract relationships. Algorithms, all they are, never forget that, like, the definition of an algorithm is just an ordered set of instructions. That's it. That's all an algorithm is. If it helps your brain, whenever I think of algorithms, I think of recipes. Literally, like, numbered steps that some type of resource in the recipe situation is probably you and your hands, will follow to accomplish a task. So if a data structure is a collection of data, then an algorithm is a process we run on that collection of data to achieve a certain end. So in the graph context, right, like if we have a graph, which is our data structure perhaps, like our adjacency list is our data structure implementation of a graph, then we run Dijkstra's on that graph. We're trying to get out a piece of something that is true about that graph, which would be a shortest path. Types of different sorts. So There are comparison sorts where you're going to just look at two elements and you're going to compare which one should be ordered before and which one should be ordered after. These are called comparison sorts because they require that your object implements the compare to method. So in the case of, say, like integer values, the compare to method might seem very straightforward because we know the numbering of mathematical numerals, right? Like we know that 1 is supposed to come before 2 is supposed to come before 3. We also probably inherently know the ordering of, say, the English alphabet, right? Like we can alphabetize A comes before B comes before C. But when we get to more complex objects, you need that compare to method to determine who comes before whom. So let's say, for example, we have a student object. Do we order by last name? Do we order by student number? Do we order by date entered the university, right? All of those different things are possible ways that could impact the ordering of a set of students, and you would need the compare to method to be implemented so that when we run these types of sorts, we can determine who comes before whom. That's what a comparison sort means. There are another set of sorts called niche sorts, sometimes called linear sorts. And those are not based on the compare to method, but rather are sort of like specifically implemented for any individual given object. I bring these up because I'm going to, after this slide, completely ignore the existence of niche sorts. But whenever I do that, there's always somebody that's like, but Casey, what about this? And I'm like, you're right. That's not the category I'm talking about. The thing about niche sorts is they're not general purpose. Those are the kinds of things where like maybe I did build it specifically into my student program or something like that. Comparison sorts, because they leverage that compare to method, which the compare to method is the only requirement for you to implement the comparable interface, if you remember that from Java. That is what indicates this item is thus something that could be used. And it also gives us this level of abstraction that now we're going to just talk about these algorithms that can be used to compare kind of anything. So comparison sorts are our general purpose comparators. For our runtimes, to be correct, just FYI, that does mean we're calling compare to every time we make a decision. So if you are going to be the person implementing compare to, make sure that it runs in constant time. It would be pretty, I don't know. Pardon me. It would be pretty intense if you ended up with a compare to method that ran in like linear time or something, but I just also call it out so that when you're thinking about the runtime, keep in mind there is a call to compare to underneath the hood. Okay. So now we're zooming in on comparison sorts. Here are some of the ways that we evaluate or compare different sorts to one another. So within the category of comparison sorts, there are what we would call in-place sorts. An in-place sort is a sorting algorithm that does not require extra memory to run the sort. So what I mean is and I don't know why, maybe this is the teacher in me, but whenever I'm imagining sorts, I always imagine like I am holding a big stack of your midterm papers, because this is my lived experience. And then maybe I need to sort them. An in-place sort would be if I was holding them in my arms and I was just sort of like flipping them around this way, so I didn't need any extra space. A not in-place sort would be one where maybe I'm running around and I'm making piles on the ground and sort of spreading out the papers. I'm using all this extra space to kind of see how things shake out. You can imagine that in that same analogy, we are going to have sorts that may or may not need the extra space to sort of organize things, and some sorts that can just sort right there in place of the original container of the data. So for example, a lot of these sorts, I'm going to give you an array of items to sort. An in-place sort is one in which we're just going to move things around in that original array. So we don't have to duplicate the memory. Ends up being a really important thing to track because some of these sorting algorithms can get really memory expensive, as it turns out. So in-place sorts, that's one of the things we need to keep an eye out for. Now, the other thing we're going to keep an eye out for is something called stability. And this is one of the things that tends to confuse a lot of students. So what do I mean when I say stability? What I mean is that if we have two items that should be sorted together, like they're duplicate items, for example, in a stable sort, duplicate items will end up in the same relative order after the sort that they were in before the sort. Let me show you an example. So, here I have a collection of 4 items. These items have sort of like 2 pieces of information associated with each. Now, I'm going to run sort, and I want to sort these items based on the number value. But I'm kind of ignoring the animal word value. And you can see that originally, the 8 that was associated with fox appeared earlier in the array than the 8 that was associated with cow. They're both 8s. So if I'm sorting based on numbers, then technically it doesn't matter which 8 comes first, but in a stable sort, the 8 that was originally earlier will remain earlier than the 8 that was originally later. So they maintain their original relative ordering for duplicate values. An unstable sort would not guarantee that, and we may or may not end up with the original relation ordering, or they could accidentally be flipped. So this is a stable or unstable example. If you're like, Casey, how can we tell if something is stable if it only has one item to sort on? In that case, you can't. Stable sort specifically is something that we always are really caring about when we're looking at an object that probably has multiple ways to sort it. Let me give you a really specific to me and very, very real example. In Canvas, when I go and sort students, it sorts by last name. You can imagine we have many duplicate wonderful last names across these classes. In Canvas, that sort is stable. So when I sort, it sorts first by last name, then by first name. Really helpful, right? Grade page, which is the thing that I go and submit your grades in, which you never see, it has an unstable sorting algorithm. And whenever I sort by your last name, the order in which those people with duplicate last names show up is just spontaneous and never seems to match the Canvas sorting order. It has taken, I will be real with you, years off my life going through and double checking what the grade page's sorted order is compared to Canvas. But Canvas employs a stable sort. It sorts first by your last name, then by your first name, and it always sorts both alphabetically, perfectly, predictably. Grade page, I'll give you an example of which sorting algorithm I think it's using, but does not offer me the same kindness. So there is a reason stability does matter. It burns me every single quarter, but you will find this comes up a lot too. I will mention whether each sort is in place or stable from here on out as we start to dig into each of the individual sorts. But does anybody have any questions about these 2 aspects of sorting? Yeah. Is there any reason to use an unstable sort? Yes, because you will find I'm going to now go through a bunch of different sorting algorithms, and like everything in this class, there is no one right answer. There is a sort that will be best suited to your individual situation. So for example, an in-place sort might not maintain stability, but maybe you care more about memory than you care about stability. Or maybe you care about speed more than you care about stability. Or maybe, you care about ease of implementation more than you care about stability. And so there will be a lot of different ways in which we are going to evaluate which sorting algorithm we use when. And I will tell you that that is your exercise 6. Your exercise 6 is given a bunch of different things you need to sort, pick the algorithm that fits for that. Any other questions about these 2 aspects before we dive into the algorithms? Oh, speed. Thanks, Pass Casey. Yeah, also speed is the big thing that we will be considering as well. Some of these algorithms run faster than others. here is some of the sorts. We are going to talk about quick sort, merge sort. We're going to talk about heap sort, insertion sort, selection sort. But there is also bubble sort, BOGO sort, bucket sort. There's something called stack overflow sort. There's also something called rainbow sort, which is, I am pretty sure, literally somebody takes your code and converts it into light wavelengths and then passes it through a prism and then recollects those light wavelengths, and that has thus sorted your information. You might be like, Casey, what is the point of bread sort or simple pancake sort or spaghetti sort? And I would tell you, I don't know. But maybe you out there will invent some new delightful sort that all of us engineers will think, isn't that hilarious and also useless? And forever you will be memorialized in computer science. So, thank you for your contributions, the incredible designers of patient sorting, or some of these are very useful: flash sort, postman sort, bead sort. I put these on here honestly so you can go Google them if you want. Some of them are fun. Okay, let's see. I will say, also, if this is the kind of stuff that you love talking about, I will mention more of this on our last day of lecture, but technically the class that follows this one is called CSE 417. It is a non-majors course, and it is really all about algorithm design and analysis. So if you really like this, please feel free to take that class. Cool. Okay, so some design patterns. Algorithms don't just come out of thin air. Maybe in the beginning, people dreamt them. I don't know, geniuses. But there are some pretty common patterns we use when we are designing new algorithms. So the first one, and the first category of sorts we're going to talk about, is the idea of having some invariants. And so the invariants have like a list of requirements, and then the idea that we're making iterative improvement while maintaining those invariants is one sort of category of sorts. I will give you an example to that. That's rarely where we're just sort of running our algorithm directly on our, say, array that we pass in. Another whole category of algorithm design can be, hey, do we have any existing data structures that already sort our materials in a certain way where we can just dump our information into a data structure and let the data structure do whatever sort of structuring, relationship management it needs to do so that we can get our sorts. And then our final design pattern that we're going to talk about together is called divide and conquer. This to me is the core of all of engineering. If you ask me what a computer engineer is, I would be somebody that knows how to divide and conquer, because what is engineering but inherently taking any given problem and breaking it down and breaking it down and breaking it down until you get to a 1 or a 0. So that will always be one of our main design patterns. We will also apply that when designing some of these algorithms. Okay, principle 1, invariants or iterative improvement. The core idea here is that we're going to start with an initial state. That initial state will be unsorted, and with each iteration or each step, we are trying to improve that state by taking it from totally unsorted to totally sorted, one little improvement by one little improvement. This is like the equivalent of like baby steps. Each step, we just make it a little bit better, is kind of the idea behind this algorithm. Okay. All right. So, one way to think of this is after k iterations of the loop, the first k elements of the array will be sorted. Let's make that sort. Okay, here's your first sort. It's called selection sort. So here is an example of selection sort halfway through the process. As you run selection sort, what you're going to do is you're going to divide your initial collection of data into what we call the sorted set of items and the unsorted set of items. Initially, all of the items will be considered unsorted. And then we will run an iteration, and what we are going to do is we will look at our sort of current item, we will look at the rest of the unsorted items, and then we will find which item belongs at the current position, and I will swap those items. So what I am going to do essentially then is from the very beginning, I'm going to look over everything in the list. I'm going to find the absolute smallest thing in the list, and I'm going to swap it into the position I know that it ultimately belongs in. So what was originally at index 0 is going to go over to wherever the thing was, wherever I found it. I don't really care about that. But I'm sort of looking through my entire list and selecting what belongs in the position I'm currently working on, and then I swap it into that spot. I think these animations are a little funky, but you can see there's another iteration of it. So in this example, I have already sorted 2, 3, 6, and 7 at the very beginning. I'm ready to go through and find what belongs at index 4. I would look over 18, 10, 14, 9, 11, 15 and find what is the next smallest thing. I'd realize that it's the 9. So then I would take 9 and 18 and swap them, and then move over to index 5 and be like, okay, what belongs at index 5? I look through the 10, the 14, the 18, the 11, the 15. I find that the next smallest thing already was the 10. Wow, it's already exactly where it belongs. Great. So I'm going to leave it there, and then I move over to index 6. And so really I'm going index by index, searching through the entirety of the unsorted items until I find the thing that belongs there, and then I swap it in. Let's enjoy this incredible artistic dance troupe. This is real, okay? This is real. This is an incredible group of humans. I'm not exactly sure where in the world they are, but I suspect somewhere in Eastern Europe, because they have built native folk dances from various Eastern European cultures, specifically to demonstrate sorting algorithms. Their incredible name is the Algorithmics. You should watch their YouTube channel. It bangs. Let's go. All right. Ooh, do we want the music? Yes. Okay, wait, let's see if I can. Will you let me share this music? Because this is way more hilarious with it. Why would you not do this, computer? Okay, but you can see what's sort of happening is, oh, they are considering, should I swap with you? Should I swap with you? Oh, maybe, yes, I don't know, aha. And then the 0, I believe, is looking, do I swap with you? And then they're like, no, 1, you are smaller than, or larger than me. And then checks, hey, 8, should I swap with you? Are you what belongs at index 0? Which happened to be this gentleman here originally. And the answer is no. Okay, 7, do you belong at index 0? No, back to your spot you go. And we continue. We do this delightful dance. And then eventually you can see, hang on, let's see if we can find where 0 is like, it's me. I belong at the beginning. Do your jig. Yes. And then he goes back to his original spot. Now it's 3's turn. And she's like, okay, who really belongs at index 1? Do you belong at index 1? And we're like, oh, actually, 1 is smaller than 3. So right now, we think this value of 1 is probably what belongs at index 1, but she's got to go through and she's still got to do her partner dance with every other number to find if she truly is the final element that belongs at index 1. So she's going to go through, she's going to do all her dances, and then we're going to find out eventually that actually she is who belongs at index 1, and she will do her jig, amazing, and she will go back to index 1, and then it's 3's turn, and she's going to find which person belongs ultimately at index 2. Any questions on how selection sort works? Yes?
So is it that like each time you find the min value, you do the swap, and then that min value goes and like continues?
Yes, so essentially this little like sort of comparisons that they're doing right now, you can think of these little moments of dancing as them comparing themselves to another one. They're looking for the next min value. And then once they've realized who is that min value, they swap the min value with whomever was currently sitting at that index that it now belongs in.
So does it swap like each time they find a small value?
Oh.
So I saw the,
Did they do that? Did they swap each other?
yeah, I think they choose like first.
And I will say, in our like mathematical or in our code representation of it, no, we only do the swap once we've determined. Essentially, you just loop until you find them in value, you keep track of that, and then you do a single swap. Any other questions for how selection sort works? a great idea. It's this, right? Oh, let's go. Hey, there we go. Okay, yes, the joys. Oh my gosh, amazing. And if you're like, Casey, do you have a video of these wonderful humans for every sort? Yes, I do. So I will let y'all continue to watch the algorithmics. I will also say YouTube is full of delightful visualizations of the sorts. So that is selection, but let's talk about selection and how it functions a little bit. So here's some code so you can look at it. My question to you, what is the worst case runtime of selection sort? What do we think? So if we look at our code, we can see that we have for the entire list, find the next minimum value. And if we look at find the next minimum value, that also has a for loop inside of it. Yeah? N squared, I agree. Selection sort is a canonical n squared situation. Now, my question to y'all is, if n squared is the worst case runtime, what is the best case runtime? Ah, wow, okay. Good job, y'all. I thought I could trick you. Yes, so selection sort has the exact same runtime for both best and worst. In fact, it doesn't make a difference. One way to think about what may trigger a best case or a worst case is how sorted the list already is. So if your list is already sorted, chances are that is going to incur the least amount of work as far as the act of sorting it goes. And so when I'm thinking about best case and worst case in regards to sorting, I ask myself, does passing in an already sorted list create a different runtime from passing in, say, a random sort or a reverse sorted list? Those are usually the cases that would trigger a best or worst case. But in this case, saying the word case a bunch of times, but in this situation, it runs n squared regardless, because no matter what, we still have to loop over absolutely everything in the unsorted set to find the minimum value. We can never look at a value and be like, that's it, that's the minimum value. We have to always consider everything in the unsorted section. So then our in practice runtime is also n squared, as you can imagine. N squared, n squared, or n squared. Yeah. Could it be n to the factorial? I am not sure where the extra factor would come in. In this case, this is a pretty canonical n squared because it's a for loop inside of a for loop, if that helps contextualize. Yeah.
What the basic idea is, we know that we'll have to go through n iterations because we're sorting n stuff.
Yes.
And for each of the n stuff, it's checking its index minus one number of things. So it's a factor would be n times n over 2.
Yes. Yeah. Yes. Okay. Maybe this is an easier question. Is this an in-place sort? Does this need any extra memory to run? No. You're right. This is an in-place sort, which is nice about selection sort. What about stability? Do we think this is a stable sort? Yeah. It does seem like it's very predictive in the way that it sorts. But actually, I'm going to show you a situation where it breaks stability. Yeah.
Is the comparison operators where it's less than it would be stable sort, but it's less than?
It's actually because we're doing swaps. And if we swap something out, we might end up accidentally swapping it again. And I will show you an example of that. The compare to, less than, or equal to situation, usually it's always less than or equal to is usually the operator we're using there. Let's look at an example. So here we have two values of 5. I added a little a and b next to them so you can keep track of which one's which. And so you can see initially, what if 5a was at the very beginning and we had to swap 5 out with the minimum value, which was actually 2? In that situation, then the original 5 ended up behind the second 5. And so then when we continue to loop through, we might end up with those two things in reverse order. So whenever, and if this helps, whenever you're doing swapping, it is unlikely that you will have a stable sort, because that means that you are altering the position of two items, including the item that you're essentially just moving out of the way of the thing you're trying to sort. And because you're just, we don't really care where the 5A originally ended up. We just meant get out of the way of the two, right? In that situation, that means we might not be preserving the original order. So selection sort, not stable. How about another one? Okay, insertion sort, often referred to as like the cousin of selection sort. The way this one works is you can see it looks really similar. We also have this idea of like, we initially start off with everything is technically in the unsorted list and nothing's in the sorted items list. And then again, because we're doing this iterative style, we're going to run some number of times and we're going to slowly grow the sorted portion of the list and shrink the unsorted portion of the list. So the way that this one works is when I am looking at a current item, I am going to start at the beginning and I'm going to look at which item is the first element in the unsorted section. So right now, 5 is like the next item to be sorted. And instead of thinking about like which item belongs in this position, which is what selection sort did, instead we're going to look at the item that's next to sort and ask, where do you belong? And then we're going to pick it up and insert it into the spot that it belongs and shift everything over. So we looked at the 5. We then looked through our set of sorted items and we realized the 5 belongs between the 3 and the 6. So we inserted the 5 between those two, and then the 6 and the 7, they all got kind of shifted over to the right. Also, this is like a weird typo. Sorry about this like 1 hanging out there. Let's do it again. So now we're going to ask ourselves 8. Where does 8 belong? And now this one's a little interesting. Where does 8 belong in this sort of iteration right here? It belongs there, right? Ignore the arrows, things are off. So literally all that happens is we just mark 8 as like, sweet, it's in the spot it belongs in. Great. So I didn't have to do any insertions at all. So what that means then is imagine what this sort would do if everything was already in its initial spot. Should we watch the algorithmic stance? Let's watch the algorithmic stance. Okay. Man, I really want... It feels like I should be able to tell this thing. Can I do maybe advanced audio controls? Uh-oh, I found them. Okay, I have no idea how loud this is going to be. What do you think rack aux is? Okay, I'm going to turn off these and hopefully... we will hear some sound. Let's see how this goes. Wow, that did nothing, computer. Okay, yes? You're right. You are absolutely right. Teamwork makes the dream work here. Oh. Yes, success. Okay, here we go with the algorithmics. I feel like we should watch them speedy. So there they go. Okay, so what's happening here is, okay, she's in her spot. Now it's 8's turn. We ask 8, where do you belong? Oh, we realize 8, you should swap. And then we realize, hey, we've got to do these kind of swaps as we go. Because 8 is trying to find, oh, there we go. 2 needs to keep going. 2 needs to find their way down. We ask 2, nope, 2 stops. So what's happening is 5's gonna ask herself, am I smaller than you? Yes, swap. 7, am I smaller than you? Yes, swap. 3, am I smaller than you? No, stay. 4, am I smaller than 8? Yes, swap. Am I smaller than 7? Yes, swap. Am I smaller than 5? Yes, swap. Am I smaller than 3? No. And that's how the insertion's happening while we're shifting. And then finally we do 6. And 6 slowly makes their lovely way down. There we go. And then, whoop, we hit our end. Amazing. Celebration, we're sorted. Oh my gosh, there's so much dance left. Wow, I'm going to be real. I've never really watched it to the end, but I will leave that for you. What joy. What rapture. Okay, let's talk about insertion sort. So, again, here is some code for us. So we can see when we call insertion sort, we're going to loop over the entire list. We ask ourselves, if the current item is smaller than the largest sorted item, then we want to find that item spot. That's the little journey that the dancers were making down the list. And then we will shift that item in. And so you can see that find spot method. There's that for loop that's going to loop over the sorted list. So selection sort was sort of like keeping that, like looking at the item between the sorted section and the unsorted section, then looking over the unsorted list. Insertion sort is looking at that item and then looping over the sorted list. So it's looking over the other half of the array. So what do we think the worst case runtime is of this sort? Yes, I agree. We've got our nested for loops. Now, remember what happened to that 8. What do we think the best case runtime is? Ah, yes, I can't trick you guys. Amazing. Yes. So if I pass an already sorted list into insertion sort, what it will do is at every item, it'll look and it'll ask itself, hey, is the current item smaller than the largest sorted item? And if it's already sorted, the answer will be no. And so then it will just fail that if statement and it just won't even bother to go into the second loop. So the best case runtime for insertion sort is if it is already sorted, you can incur that end runtime. In practice, if you are in an interview or you're talking to another engineer about it, you generally talk about insertion sort in terms of n squared because we are pessimists when we talk about runtime, and also it's pretty unlikely that you're going to call sort on an already sorted item, but it is a pretty unique and helpful feature of insertion sort that it runs more efficiently on a list that is more sorted already. What about in place? Is this an in place sort? Yes, I agree. Yep, we're just swapping things around in the array. What about stable? Is this a stable sort? Ooh, yes. I agree. Yes, this is a stable sort. In this case, we are not doing those sort of swaps. We're just like throwing somebody out of the way. Instead, we're looking at each individual item as we come to it in its original order and then selecting like into a spot, inserting into its spot where it belongs. So it is a stable sort. Here is an example with those 5s that we did before. So for example, the very beginning, we would mark anything in the very beginning will remain in its original spot because we have nothing in the sorted collection. And then we'd look at the 3 and we'd ask, hey, is the 3 smaller than the 5? Yep, so that 3 gets swapped in there and 5 will stay in its original orientation. But then when we eventually get to the 5s up against each other, when that second 5 sees that first 5, it is not smaller than, so we will not incur a swap here, so these 2 will remain in their original relative orientation. Any questions so far about insertion or selection sort? So one thing that is nice is that these sorts are iterative, right? Like I said, that's sort of the collection they're in. So let's say, for example, you only needed the first 5 items to be sorted, and then you just like don't really care what's happening after that. You can kind of bail out of these partway through. You'll see as we get deeper into the sorts that not all of them are true like that. A lot of them you have to sort of wait until it's totally done for everything to be in sorted order. So that's one thing that can also be nice. So let's move on to our second category of algorithm design patterns. If only we had a data structure that was really good at getting the smallest possible item remaining in our data set. Any ideas what that data structure might be? Heap indeed. So welcome to Heap Sort. We already have this data structure that hopefully you've built and are now very convinced is quite efficient because we implemented it with an array, which is great. And a heap's job is to keep the minimum value quickly accessible at the top. And if you remember, we learned about that thing called Floyd's build heap. that runs an n runtime. So we could take a huge set of items, run Floyd's build heap on them, and dump them all into a heap, and then just call remove min n times. Should we watch the algorithmic stance? Let's see what they do for this one. Honestly, I don't know how much I've watched this one, so we're going to see. Okay, this is apparently a Hungarian folk dance. Wow. Ah, look at, they've drawn the tree for you. Amazing. And so you can see what's then happening there is huzzah. There's hats involved in this one, and I'm not entirely sure why. I also thought that tree was an animation. Apparently it's real tape on the floor. So here you can see what they've done is this is their Floyd's build heap. They are currently deciding who becomes the parent of whom, and this is them doing a swap. This is their percolate up. Now it is time to decide, is 7 the proper parent for the 4 and the 5? And right now they're deciding who is the right. There we go. And we're like, maybe? Wow, there's a lot of spinning in this one. Okay, this is a max heap. It looks like what they're doing for context instead of a min heap, but the principle still applies. We're deciding who is the right person there. We have now realized that 7 is the larger of the 2 children, and we are deciding whether or not the child and the parent should swap, and we realize that they should, and then eventually, huzzah, couple 7 makes their way to the top of the heap. Yay, there we go. My goodness. There is still so much dancing. Ah, yes, we're fixing this parent relationship. Okay. And this, I believe, is an example of remove min, and off they go. Goodbye, couple number 7. And so we swap in from the bottom rightmost. That's what just happened. We replaced the overall root, and now we're picking which of the children does the overall root get replaced with. And we are then percolating down the 1 is what's happening. And there we go. 1 percolates down, and then theoretically 1 and 3 will continue to percolate down, so on and so forth. Oh, okay. There we go. Amazing. It's the heap tree in stage tape that really does it for me, honestly. Huzzah! Okay, and then there's another remove min! Huzzah! Amazing. So, I will leave it there. We'll come back on Friday. I'm going to talk to you about some of the different ways we can implement Heap Sort that makes it especially efficient. Go to Section Tomorrow. Section Tomorrow is really going to help you with your answers to Exercise 6. Also, we threw in a question to help you with P4. So Section is especially designed this week to help you do your assignments. Thanks so much, everybody. See you on Friday.